Hi, I'm Gary Yuan, and this is a user's guide and features presentation to ESTEST given originally to the Gali group on August 24th, 2011. This talk is going to be more for the perspective of end users, and so it'll be a little bit of background on ESTEST, but mostly consisting of user tutorials. So to begin with, we consider simulation codes. And in fact, there are lots of simulation codes in electronic structure. These codes have different formats in terms of I/O and different code bases and user communities. Some of these simulation codes would use pseudopotentials, while others are all electron. Some use plane waves, while others could use linear combination of atomic orbitals. Most of them are free and open source, but some of them can be for profit. Into this field of electronic structure, we've developed ESTEST. That is a platform to collect and organize, format, verify and validate, compare, post-process, and enable collaboration on the information in electronic structure. Well, and in order to do these things, we must first ensure that all this information has a common representation. And this is the process of translation by which we take Python to translate things that look like this into something that looks like this. And this translation process is completely customizable to take any format in plain text, CML, XML, or binary into the unified representation that is the URXML. So just speaking a little bit more detail about the URXML, well, the Unified Representation XML format is one that we develop internally with ESTEST and is completely documented with a full XML schema associated with it. We get several benefits from using the URXML in addition to having this unified representation of all the code I/O and the information associated with that. In terms of the document itself, it's completely extensible to represent new kinds of information from the science that we would like to represent from the simulation. It also gives us very specific units and standards defined for all these information elements. So for example, energy will be given in units of Hartree, and coordinates will be typically given in Bohr. It also reproduces the original I/O in the entirety, and it represents both simulations and publications. So to the left, I've shown sort of this cartoon representation of a URXML document. That is, it consists of 3 sections. The first one for being annotations to the document itself. Think in terms of keywords and abstract. The next section is for the URXML data that contains all the parsed information from the original simulation code I/O. And then the last section is called QM data. Contains the original I/O reproduction itself. And every URXML document is going to have associated with it a UUID reference that is completely unique to that document and specifies it in our database. So so I've said that our database consists of URXML documents, but the database software itself that we use is something called ExistDB. And for an end user, it's not important to know what Exist is, in that it does run completely in the background. But I'll quickly mention that it does run on xQuery, and it handles the transform of the XML documents. In terms of the user experience itself, it's nice that it handles this XUpdate plus XML plus retranslation process, in which any document that is written in an older schema is automatically updated to the latest version of the URXML schema completely seamlessly and without any user intervention at all. Okay, so just a little bit of summary of what we've gone up till now. We've really treated the data flow of information in ESTEST. That is, we start with the original code simulation I/O input and output documents. We pass that I/O into our translators written in Python that'll translate these formats into the URXML document format. With our collection of URXML documents, we put these into an xQuery and XML database. Now, in terms of the end user experience, we really don't need to worry about any of those parts. And what we're going to do now is to go into the web client interface to these parts of ESTEST and begin a series of tutorials to show what you as an end user can do with ESTEST. Switching gears, we're going to start off with a bit of preview for the tutorials to come. Again, we're going to follow the logical progression of data through ESTEST, starting out with upload, that is getting simulation I/O documents as well as publication records into the ESTEST database. The document manager then is going to allow you to organize that data that you upload, and search is going to allow you to find other users' documents that they may have uploaded. A view of any URXML record is going to give you a transform of that record in a format that you can read easily in a web client, and gives much more detail about the data contained in that document. Comparisons between two or more URXML documents are very useful for comparing a related collection of documents. And then we're going to end out with plugin processing that really extends the capabilities of certain comparisons and visualizations, as well as other processings that you can do on URXML documents as a whole. Switching out with, let me just say a little bit about how to upload documents to ESTEST. You can upload simulation files individually, 5 at a time, to the ESS server, or you can bash them together in an archive in gzip or tar format, and that can hold any number of simulation files in their separate directories that will be crawled through by the translators themselves. There is a post limit restricted to 10 megabytes for the size of each upload, so you have to be mindful of that. The way we upload publications is by giving input a DOI reference number to the publication, and then you will need a cross-reference PID registration that you can get at this URL seen here to be able to successfully upload the publication as well. So let me just switch to just a simple example of how to upload a document. Here we see a landing page, which is basically the account manager for any user of ESTEST. This is what you'll see by default once you log into the system. To upload a document, we'll just go to the Create button. This will bring up a separate window which has two options to proceed, either upload a physical simulation or a publication. Let's just go over to see a publication for instance. Here you'll see the what I meant by the cross-reference PID is usually just an email address, and then you would enter in a DOI number directly here. But first, let's just start with a physical simulation. We can choose the simulation tool you want to translate with. So I mean, this is the simulation code that you pick for whatever upload you're making. So in this case, we'll just say QBox, and then go to Choose File. We have a bunch of files already set up here, and in this case we have an archive that's QBox files. We choose that archive. You can click this to sort of help with the naming of files by default, and so we'll click that and then say Submit. And so we'll just wait a little bit here. And now it says it's uploaded the following 5 simulations, which is what we had in that archive. So we can close this and then refresh this page here to see our new uploads, which will appear in our document manager that we can navigate through. And we have our 5 simulations uploaded here. Okay, so just moving on, next I'm going to describe the ESTEST Account Manager interface and all the different actions that you can take on the documents that you've uploaded. But first I just want to emphasize that when you see this hierarchical file view of your documents that are indented based on the / tokens in the file strings, these file strings are stored internally in the URXML document itself, and they don't have any correspondence to how the data is actually laid out in the XML database. So what this means, for example, is that you can have naming collisions in which 2 of your files are named exactly the same thing, and it won't have any ill effect except for the fact that you can't distinguish them when you view them in the file manager here. But if we just go back to our account that we've set up before, I'm going to describe each of the actions that you can take on the directories as a whole, and as well as the individual document actions that correspond to 1 or more URXML documents individually. So the first thing we can do is to rename a directory to something a bit more sensible. So this one was corresponding to the QBox simulations files that we've uploaded, so we can rename this with a QBox root, for instance. So we see here now that all these documents have been renamed. The next action we can take is to check all or check none of the URXML documents individually. And this is going to be useful to go through the individual document actions. So for example, if I check these two silicon simulations and then click the relate button, what this is going to do is to create a bilateral relation between all of the URXML documents currently checked. So for example, if I click relate here, it's going to make relation between SI4A and SI4B. So if I view SI4A, it's going to have the relation to SI4B. If I view SI4B, it's going to have the corresponding one that is to SI4A. So if we go back now, we can rename any of these files individually as well. So this is going to bring up a pop-up window to say rename the file. And if we refresh, we can view that rename. Again, you can check these individually and then go to compare, and this is going to basically launch the compare web page for ESTEST, and we'll describe this later in more detail. We can check more documents and go to download, and what this is going to do is to provide a tarred archive of the raw URXML data itself for all the simulations that you checked, so you can have a local copy of the data that you've uploaded to ESTEST in the URXML format. The last button, again, is sort of similar to compare. It's going to navigate you to the plugins landing page, but with the data based on UID reference already initialized based on the documents that you've based on the documents that you checked. So again, this is going to initialize it for each of the plugins itself. And I suppose the final sort of document action we can take is to delete the entire directory itself. And this is sort of irreversible, so you have to confirm that, okay, we want to delete these. And we see here that we've deleted our simulations. Okay. So suppose that you, as an ESTEST user, have uploaded some simulation documents and the other users have uploaded their simulation documents. A natural thing we want to do is to be able to search through the database and find documents that we're interested in. And so I'll describe the aspects of search next. The first thing we can do, again, is we've named our files based on some conventions, and so we can search based on these file substring matching criteria. So if we just go to the ESTEST homepage and search for any particular file string, for example this one that I know exists, we can search that and find all the documents corresponding again to this file prefix that we've been searching for. We can also search for documents based on keywords. So if I go back to our search and say I want to have documents based on the espresso keyword, I can click keyword search and then again search, and then this is going to basically return all those results. And so this is sort of equivalent to doing a keyword search based on this keyword cloud. Again, if we can click, it's going to do the keyword search based on that. The next sort of search that we go over is a chemical species search. Well, this is part of the advanced search features in ESTEST. So if we go back to our web page and go to advanced search, there is that you can specify basically the search type. So a general would be sort of like the file string matching. You can specify that it's a keyword search that we've shown before. You can specify that you only want publication results. But at last we can say that we're doing a chemical species search. And the chemical species search itself has a few criteria that you can match. So if you click on this question mark, it'll go to a help page with more details on that. But basically you can say it can match any of the following species that I supply, or that it must include these species, but it can include them in that quantity and others, or it can only match these ones. So I want an exact chemical string match. So if I say only species and I say I want methane, so I want C1H4, and it is important that you add the 1 to the C just based on parsing purposes. and click search, it's going to basically return all the simulations that are explicitly methane in the atomic basis. Okay, just continuing with our advanced search features, we can also filter by user, filter by document type, as I've said, based on simulation or publication, and we can also filter by date range based on when the document was created. I'll show just an example of the first one, that is filter by the user. So if we go back to our advanced search page, and we just have some sort of generic term that we'd like to search for, say methane, but we know we're interested in a particular user, and this is based on the username in ESTEST, so you will have to know their username. And we'll go search. It'll basically return those simulation documents based on that keyword or search string belonging to that user individually. The last thing I'll say about search is that search has full cross-server support across all ESTEST servers in the configuration. So that means in the same user interface on the web page, you can search across many different ESTEST servers, provided they are in the configuration for the server that you are searching on, or the interface server, as I like to call it. So having found some documents that we're interested in using the search features in ESTEST, the next logical step is to view the documents itself to find out a little bit more information about them. So if we go to any sort of set of search results, we can click on each of the documents individually to bring up a summary page that is a transform of the URXML data for that simulation. And so this page contains a lot of more detailed information about the simulation in question. So it has links to the original URXML data, as well as plain text links to the standard in and the standard out files used for this simulation. It has some, again, the transform of the data of the URXML in terms of parameters, maybe a visualization for the atomic basis, some information about the species, including the pseudopotential reference if that's available. There are a couple of widgets to determine the bond lengths between the atoms and the bases, as well as the bond angles. The energy will be tabled based on the energy component, and a band structure will appear if that is available as well. In the view, if you're the document owner or you have sufficient permissions for that document, you can also edit the keywords, abstract, related records, and comments for that document. So very quickly, because in the account that I've signed on in as tester, that is the owner of this document, we can edit the keywords very simply by saying here, and there'll be just a quick autofill. This is just a comma-separated list. So once we're done, we can say save keywords, and then we save the keywords here. We can also edit the abstract. This is some abstract, for instance. We save that here. Related records, we've seen that before when we're talking about the account manager. It works in much the same way, except here you'll just enter in the strings of the UIDs you want to relate to. At the very end here, we can add comments. Say great document. And we'll see the document here. So, and if you're the comment poster, or if you're typically the document owner, you can also delete the comment. Or I should say that if you're the comment owner, you can delete the comment as you'd like. So say that we've found a collection of documents and that we've viewed them and we see that they're part of a collection. A very useful thing we can now do is to compare the documents in together side by side using our compare transform in ESTEST. And so for example, I've found this collection of documents that correspond to a lattice constant relaxation run for the aluminum cell. If I check all the documents that are part of this collection and say compare, it's going to launch into the comparison transform that is built into ESTEST as part of the web interface. There are several things we can do here, but first I want to point out that the simulation documents in our collection are given a numerical mapping that are corresponding to to the numbers in the columns, as well as the keys and plots and things like that. We can always reorder this mapping very simply, and using this page, you can do a manual reordering if you like, but usually you want to reorder based on maybe the name or something sensible to reorder on. In this case, since this is a relaxation, we want to really reorder based on the volume ordering. So we see here that we've ordered on the volume, and this goes to 0 to 10. And so we say save order here, and it's going to say that the order is saved, and it's going to ask you to refresh the compare page. So just say OK, and close this reorder page. In the comparison page, we refresh very quickly, and we see that the order is changed. So every comparison page is going to have this sort of general table of comparable values. You see here that it will compare the different E-cuts or the different volumes, the different energy components, as well as the stresses. The energy components are sort of interactive in the sense that they correspond to this Google plot visualization that is just a scatter plot of the data series versus the energy component. So if I click on any energy component, it's going to just filter for that one component. Scrolling a little further down, we have a sort of visualization as well as a tabled comparison for the spectrum or the band structure, in which we can select the K point that we want to compare, and this will just compare them in the columns, again corresponding to the mapping, with the first column being the key to decide which K points appear in the comparison. And this visualization as well is just showing you a sort of scatter plot of the different K points based on some sampling, and it's just an easy way to determine if two band structures are very similar or they're very dissimilar. But to get the details, again, you'd have to look at the tables for the comparison. So the last thing I'll say about compare is that, like search, it has complete cross-server support. So that means that documents in this list for comparison could be from the local interface server, or they could be from an external server in the configuration, and these documents will compare perfectly well side by side like any other comparison. The last set of tutorials are going to cover post-processing plugins for ESTEST that anyone can develop and customize. These plugins treat a wide range of applications, from band structures and plots of the density of states to visualizations of the atomic bases. There's too much detail to go over these individually, but the idea of plugins is to combine your XML data with implicit information input by the user to advance post-processing. The plugins run the gambit of operating modes in ESTEST, from offline to online on the server and across multiple ESTEST servers as well. We can actually go back to a comparison that we made before to show the first example of a plugin. Again, you're going to see this comparison of the relaxation run of several unit cell volumes for aluminum. Just from this comparison, we get a good idea of where the minimum total energy lies and the corresponding volume associated with that. But because the comparison transform doesn't know that this collection as a whole represents a relaxation run, it doesn't know to compute the parameters of the equations of state, such as the bulk modulus, for example. And that's an extension of functionality that a processing can be capable of. And in fact, we have a plugin to address that. So if we go back to the search, the landing page for search results, there's a link to say process with plugins, and that is going to redirect to the plugin sandbox page with the UUIDs for the aluminum run already initialized in the cookie that we're going to use to convey the data to the plugin. So the plugin we want is the energy versus volume fit plugin. And this is just saying that it's going to take a set of simulations, usually of varying volumes, and it's going to fit that data to the Murnaghan equation of state. So if we just say run plugin, we see that all our UUID references are already initialized into the appropriate text area input. We do have to specify that we have one data set, and all the other default parameters are fine for this example, and we just say run plugin. So it's going to take that data, and then it's just going to compute the fit to the equation of state, and we see here that we have the plot of the fit to the original data points in light blue here, and the fit in this gold color. And then this table is showing explicitly what the parameters are, including the bulk modulus and the equilibrium volume. We can actually go. Another plugin that exemplifies this idea of using implicit information along with UR/XML data is the band structure plot plugin that I'm going to show next. Whereas this energy versus volume fit plugin uses the implicit connections between the simulations in the data set in terms of varying volume, the band structure plot plugin is going to use knowledge about the data in each simulation file itself. So if I go back to the search page and I clear all the current records that I've stored for the aluminum dataset run, I'm going to search another string to find documents that I can use with the band structure plot plugin. In this case, I'm going to look at the band structures of silicon as computed by Qbox as well as Quantum Espresso. So if I check one simulation, in this case for Qbox, and go to process with plugins, I can start the band structure plot plugin in the same way and say run plugin. The band structure plot plugin is going to require a few more parameters than the previous energy versus volume fit plugin. The first thing you want to specify is the Brevet lattice type. In this case, silicon uses an FCC lattice. And then we're going to need the sample path of the k-points in terms of the symmetry labels. And this is really the implicit information that we're going to use, because the UR/XML document doesn't record this by default. You're going to need to know it beforehand. So in this case, the symmetry path is going to be L to X to W to K to G to L to U to W to L to K, and then a bar, and then a UX. Okay, you can specify a k-point matching tolerance, that is the distance of point or error in which a k-point actually matches to a point on the symmetry path. We have already initialized our UUID reference. The default is to plot the band structure itself rather than to give the symmetry path, which is the other option. You can change the unit if you like, but otherwise we can leave the HTML output option as default and say run transform. So for a single band structure, as we've input in this case, it's going to show the tables along the symmetry path of all the eigenvalues that you can compare them in this table form. And then at the very end, it's going to show you the plot, and then with the different eigenvalues colored in the keys for the band structure of silicon. There's an additional operating mode to the band structure plot plugin when you have two or more band structures, and it's going to treat those in terms of a comparison that I'll show you next. So if we close this transform and then go back to our search page, we can check again the simulation for the silicon band structure, in this case computed with Quantum Espresso, and then say again process with plugins. We're going to go back and run the band structure plot plugin, and then fill in the appropriate input information again. Leaving all the other parameters default, except in this case I have two UUIDs initialized in the text area input, and say run transform. It's going to give you an alternative view in which the two or more band structures are being compared along the symmetry paths. In this case, a table showing the two columns, and then the eigenvalues being compared side by side. You can choose any of the points along the symmetry path for this table to represent. And again, at the end, instead of coloring by the levels of the eigenvalues, we have here just coloring based on each of the two simulations, so that you can see them compared side by side in these different color schemes. So I could go on about plugins, but there are many more resources available online at our website for demonstrating how to use plugins, as well as other aspects of ESTEST. So I'll conclude this talk now and redirect you to our website at estest.ucdavis.edu, where you can find many more helpful resources, as well as contribute your feedback to our project via discussion boards or emails directly at estest.dev@gmail.com. Thank you very much.